In 1977, a golden record left Earth aboard Voyager 1, carrying greetings in 55 languages. Carl Sagan oversaw its creation personally, selecting every sound and image with deliberate care. The record contained music, the sound of rain, laughter, and a mother's first words to her child. It also carried precise coordinates pointing any finder directly back to our sun and our planet. We announced ourselves to the universe. We gave directions. We signed our name across the void. Voyager 1 is now 24 billion kilometers from Earth, the farthest object humanity has ever built. At its current speed, it would take approximately 73,000 years to reach Alpha Centauri. And Alpha Centauri is our nearest stellar neighbor, the closest thing to a next-door address. The universe is not merely large, it is incomprehensibly, structurally, permanently vast. Every attempt we make to reach outward runs into this single physical reality at full speed. Distance in space is not an engineering problem waiting for a better rocket or a smarter fuel. It is a constraint written directly into the geometry of space-time by the laws of physics itself. And any civilization that someday hears our signals faces the exact same wall we do. On September 2, 1859, the sky over the Caribbean turned blood red at midnight without warning. Telegraph operators across North America and Europe received electric shocks through their fingers. Some telegraph systems continued functioning without batteries, powered entirely by the solar storm. The Carrington event was the most powerful recorded geomagnetic storm in human history. It reminded humanity in the most dramatic possible way that space is not silence, it is a medium that carries energy, radiation, and information across unimaginable distances. And information in this medium travels at exactly one speed, regardless of how it was sent. That speed is 299,792,458 meters per second. No transmission has ever exceeded it by a single meter. This is not a temporary limitation waiting for better technology to arrive and solve it cleanly. It is a constraint embedded in the structure of space-time itself, confirmed by every experiment run. In 1905, Albert Einstein published his special theory of relativity from a patent office in Bern. He showed mathematically that as any object accelerates, its effective mass increases toward infinity. To actually reach the speed of light, an object with any mass would require infinite energy to do so. Not an enormous amount of energy, not energy equivalent to a star. Infinite energy, all of it. This is the wall. It has no door, no window, no known loophole, and no theoretical exception. Every signal we send, every radio wave, every laser pulse, every quantum communication obeys it. And every civilization anywhere in the universe is constrained by this same law without exception. The nearest star system to our sun is Alpha Centauri, a triple star system 4.37 light-years away. 1 light-year is the distance light travels in a single year, approximately 9.46 trillion kilometers. To Alpha Centauri, 41.3 trillion kilometers of empty, cold, radiation-soaked interstellar space. Our fastest spacecraft ever built is the Parker Solar Probe, which peaks at about 690,000 kilometers per hour. At that record-breaking speed, reaching Alpha Centauri would take approximately 6,300 years. The ancient Egyptians began constructing the earliest pyramids roughly 4,700 years ago. We would still be centuries from arrival. A civilization would rise and fall before we got there. And Alpha Centauri is, by every cosmic measure, essentially sitting in our backyard as neighbors go. The Milky Way galaxy stretches approximately 100,000 light-years from one edge to the other. It contains somewhere between 100 billion and 400 billion individual stars within its spiral arms. The average distance between neighboring stars in our galaxy is approximately 4 to 5 light-years. To cross the galaxy from one side to the other at the speed of light would take 100,000 years. And the Milky Way is just one galaxy among an estimated 2 trillion in the observable universe. The observable universe spans approximately 93 billion light-years in total diameter right now. These numbers are not meant to convey scale intuitively. They are meant to be computed and feared. They represent a physical reality so extreme that human cognition genuinely cannot absorb it directly. In 1895, Guglielmo Marconi transmitted the first deliberate radio signals through open air. He began by sending Morse code across a room, then across a field, then across the English Channel. In 1901, he transmitted successfully from Cornwall to Newfoundland, spanning 3,500 kilometers. He did not understand what he had done to the cosmos, but the cosmos began registering it immediately. Every radio wave that has ever left Earth travels outward in all directions at the speed of light. It expands as a sphere, growing larger and more diluted every passing second, continuing forever. By 2025, our earliest radio transmissions have traveled approximately 125 light-years from the Sun. This expanding sphere, sometimes called our radio bubble, now encompasses roughly 15,000 star systems. Within this bubble, any civilization with sufficiently sensitive receivers could detect our presence. But here's the fundamental problem that makes even this seem less impressive than it sounds. Signal strength falls off with the square of distance as it spreads across an ever larger sphere. Double the distance and the signal arrives 4 times weaker. Triple it, 9 times weaker than before. At just 2 light-years from Earth, most of our radio and television broadcasts have already fallen below. They have fallen below the noise floor, the level of random cosmic background radiation everywhere. The cosmic microwave background radiation alone drowns out the vast majority of our transmissions. Our TV signals, our military radar, our FM radio, all of it fades into thermal noise quickly. Only our most deliberately powerful directed transmissions remain marginally detectable any further out. And marginally detectable at greater distances requires a receiver the size of a planet to capture. In November 1974, the Arecibo Observatory in Puerto Rico aimed a deliberate message at the sky. Dr. Frank Drake and Carl Sagan designed the transmission together over weeks of careful collaboration. They aimed it at the globular cluster M13, a target containing roughly 300,000 stars at once. M13 sits 25,000 light-years from Earth, a distance that makes the mathematics almost cruel in scope. The message itself was 1,679 binary bits, 23 multiplied by 73, both prime numbers chosen with purpose. It encoded a pixel image of our solar system, the structure of DNA, and a rough human figure in outline. The transmission took exactly 3 minutes to broadcast, the earliest possible reply, 50,000 years. Humanity will not be the same species in 50,000 years. We may be unrecognizable. We may be gone. Drake understood this completely. He was not expecting an answer to arrive within anyone's lifetime. He was making a philosophical gesture at the cosmos, saying, "We are here, we are aware, we are trying." He was saying it to the darkness, knowing the darkness could not answer for longer than civilization lasts. The silence surrounding that gesture has a name in the scientific literature: the Fermi paradox. In the summer of 1950, physicist Enrico Fermi sat down to lunch with colleagues at Los Alamos. His colleagues were casually discussing a newspaper cartoon about UFO sightings over New York City. Fermi listened quietly to the conversation, then interrupted with a single unexpected question. He asked simply, "Where is everybody?" The table went quiet. The question was deceptively casual. The Milky Way galaxy is approximately 13.6 billion years old, plenty of time for life to develop. Life on Earth required about 3.8 billion years to produce a civilization capable of broadcasting radio. If life arose even rarely across the galaxy, there has been sufficient time for multiple civilizations. With any reasonable interstellar travel technology, a civilization could colonize the entire Milky Way. Even moving at just 1% of light speed, crossing the galaxy end to end takes only 10 million years. 10 million years is brief by cosmic standards, a weekend trip on the time scale of the universe's age. So where is the evidence? Where are the signals, the artifacts, the megastructures, the visitors? Fermi's question, asked casually over lunch, remains the most uncomfortable open problem in all science. In 2015, a star designated KIC 8462852 was flagged for unusual behavior by citizen scientists online. It showed bizarre, irregular, deeply asymmetric dimming patterns that matched no known stellar behavior. A transiting planet produces regular, repeating, predictable dips in a star's measured brightness. This star's light curve was erratic, uniquely deep, and completely asymmetric in its timing and shape. Dr. Tabitha Boyajian at Yale University published the puzzling data in a peer-reviewed journal paper. It ignited an immediate and serious firestorm across the global astronomical research community. Penn State astronomer Jason Wright raised a hypothesis that was scientifically legitimate on its face. Could these irregular dimming patterns be the shadows of megastructures orbiting the star directly? Dyson spheres are theoretical shells constructed around stars to capture their total energy output. A partially complete Dyson sphere, a swarm of solar collectors, could produce exactly this pattern. Follow-up infrared studies ultimately pointed toward clouds of dust as the most probable explanation. But the episode exposed something important about where we currently stand with this entire question. We are actively scanning the sky with every instrument we have constructed at every wavelength we can. The silence we are receiving is not from lack of effort or lack of technology or lack of commitment. The silence is coming from somewhere else entirely, from the scale of the problem itself. Let us be precise about the timeline of our own electromagnetic presence in the universe. Our Sun is approximately 4.6 billion years old. The Earth condensed from the same disk 4.5 billion ago. Single-celled life appeared on Earth approximately 3.8 billion years ago in warm, shallow, ancient seas. Multicellular organisms emerged around 600 million years ago. Technological civilization, this century. We have been broadcasting detectable radio signals for approximately 125 years out of 4.5 billion. As a fraction of Earth's existence, our radio presence represents 0.00003% of our planet's history. In cosmic terms, we turned on our beacon during the final fraction of a second before midnight tonight. Any civilization receiving our signals must be close enough to receive them before they fade to nothing. Close enough, in this context, means within roughly 2 light years for ambient broadcasts at best. For our most powerful directed transmissions, perhaps a few dozen light years in optimal conditions. The window of detectability, the distance over which we are actually a recognizable presence, is tiny. The SETI Institute was formally established in Mountain View, California in the year 1984. Its scientists have surveyed billions of radio frequencies across millions of hours of telescope time. The Allen Telescope Array in Northern California, funded partly by Paul Allen, dedicates itself fully. In the decades since its founding, SETI has found one candidate signal that has never been explained. It was originally detected on August 15, 1977, at Ohio State University's Big Ear Radio Telescope. Astronomer Jerry Ehman was reviewing a printed computer analysis of recorded radio observations. He noticed a 72-second signal of extraordinary strength originating from the direction of Sagittarius. He circled it in red pen and wrote a single word in the margin: "Wow, the signal's permanent name." Despite hundreds of follow-up observations over the decades since, the WOW signal has never recurred. Its origin remains genuinely unknown, its nature is still debated, its source has never been confirmed. It stands as the single best candidate for an extraterrestrial transmission in the history of SETI. But even if it was deliberately sent, even if an intelligent civilization aimed a beam at us in 1977, they sent it from far enough away that we have never successfully located them with any instrument. And they sent it before we had the capability to compose or transmit a meaningful reply in return. Consider now what the math actually looks like for a detailed hypothetical contact scenario in full. Suppose an intelligent civilization exists on a planet orbiting Proxima Centauri, our nearest neighbor. Proxima Centauri sits 4.24 light-years from Earth, the single closest individual star to our Sun. Its planet, Proxima Centauri b, was confirmed in 2016 by the European Southern Observatory in Chile. The planet sits within its star's habitable zone and may, under certain conditions, support liquid water. Now suppose that civilization has been listening carefully and detects our earliest radio transmissions. Here is where the timeline reveals itself, with merciless precision, and allows no optimistic rounding. Our earliest radio signals passed Proxima Centauri around 1904. They left us in the early 1900s. Anyone living at Proxima Centauri who wanted to reply has had more than 120 years to send an answer. A reply transmitted in 1910 from Proxima Centauri would have arrived at Earth before World War I ended. No reply has come either. They are not there, or they are not listening, or they cannot hear us at all, or the signals arrived too faint to distinguish from natural background noise at even that short range. Now construct the most generous, most optimistic interstellar contact scenario physically possible. Suppose a civilization at exactly 50 light-years distance detects our transmissions clearly in 2025. They immediately begin composing a response and simultaneously launch an interstellar probe toward us. They give this probe their maximum achievable velocity. Let us say 10% of the speed of light. 10% of light speed is an extraordinary achievement far beyond anything humanity has built. Reaching it would require more energy than the total energy output of human civilization throughout history. At 10% of light speed, covering 50 light-years of distance requires exactly 500 years of travel time. The probe launches today in 2025. It arrives at Earth's location in the year 2525 at the earliest. Their signal informing us a probe was launched travels at light speed. We receive it in 2075. We would spend 450 years knowing something was coming before it finally arrived to meet us here. But here's the part that makes the entire scenario collapse into irresolvable philosophical tragedy. That civilization aimed their probe at Earth as it was in 1975, 50 years ago when their signal left. They aimed at a world without smartphones, without the internet, before the personal computer existed. They aimed at a species they observed living through the Cold War, not the civilization we are today. By 2525, humanity could be extinct, unrecognizable, transformed beyond all biological continuity. The probe would arrive carrying a message addressed to recipients who no longer exist in any form. It would be the cosmic equivalent of a letter addressed to the Roman Empire arriving today by courier. The specific content of humanity's expanding radio bubble deserves very careful and honest examination. Our earliest transmissions were Morse code and primitive AM radio from the very beginning of the century. By the 1930s, early television signals began escaping our atmosphere and heading outward into interstellar space. In 1936, Adolf Hitler personally opened the Berlin Olympics in a ceremony broadcast over television. This was among the first high-power TV transmissions ever sent, and it went everywhere at once. It is now approximately 89 light-years from Earth, still traveling, still carrying its original content. The first impression any alien civilization receives of human cultural achievement may be a Nazi salute. This is not a comfortable thought, but it is the precise, unavoidable mathematical reality we inhabit. By the 1950s, Lucy, Ricardo, and Ricky were arguing in their apartment and leaking outward into the cosmos. By 1969, the signal from Armstrong's first step on the lunar surface expanded outward at light speed. That moon landing signal is now 56 light-years from Earth, still spreading, still thinning with distance. A receiver at Proxima Centauri today would detect it theoretically, but barely above the thermal floor. Beyond perhaps 1 to 2 light-years from its current position, the signal dissolves entirely into static noise. Our most celebrated and historic moment, humanity's first step beyond Earth, reduced to silence in 2 years. The SETI scientist Dr. Jill Tarter has spent more than 4 decades working on this exact question. She co-founded the SETI Institute, and her life's work directly inspired the Carl Sagan novel Contact. She makes a distinction that matters enormously when thinking about what we actually are to the cosmos. We are not a beacon, she argues. We have never been a beacon. We are something far more modest than that. We are a leak. Our transmissions escape into space by accident, not by intention or design. Radio, television, radar, all of it bleeds through the atmosphere and spreads outward into space. Its content is incoherent at a civilizational level. Fragments of entertainment, military radar pulses. If any civilization is attempting to decode it, they face a signal that looks like radio frequency pollution. Billions of simultaneous, overlapping transmissions in hundreds of different human languages and formats. From the outside, our civilization does not look like a communicating intelligence. It looks like noise. In 2017, the journal Nature published a landmark paper on the analysis of exoplanet atmospheres in detail. Using the Hubble Space Telescope, scientists detected specific molecular signatures in a distant planet's air. This technique, transmission spectroscopy, analyzes the chemical composition of a planet's atmosphere. We do not need to travel to a world to analyze its air. We can read it from light years away in principle. If another civilization has this technology aimed at Earth, and it requires no exotic physics to build, they would detect oxygen, methane, and nitrous oxide coexisting in our atmosphere simultaneously. That specific combination of gases cannot persist naturally without biological processes renewing them. They might know with certainty that Earth hosts life without having received a single radio broadcast. They might have known for millions of years, long before we evolved, before we stood upright, before fire, before language, before the first human hand pressed against a cave wall and left its outline in red ochre. And still, across that entire span of detectable biological Earth, nobody has come to investigate. Either nobody is close enough to care, or the distance is stopping them exactly the same way it stops us. In April 2016, physicist Stephen Hawking and entrepreneur Yuri Milner announced Breakthrough Starshot. The concept was to accelerate gram-scale light sail probes to 20% of light speed using a ground laser. A 100-gigawatt laser array would push a postage stamp-sized sail across the interstellar medium. At 20% of light speed, such a probe would reach Alpha Centauri in approximately 20 years of flight time. The project attracted serious physicists, Nobel laureates, and substantial funding from the beginning. The engineering challenges became apparent immediately upon serious technical analysis of the plan. At 20% of light speed, interstellar dust grains strike the probe with the force of tiny explosive charges. A grain of sand at that velocity releases energy equivalent to a hand grenade detonating on impact. The required shielding material does not currently exist in any laboratory or manufacturing process. The laser array itself would require energy output roughly equivalent to total global electricity production. The targeting precision required is extraordinary, aiming a beam at a star moving across the rotating sky, and the probe, once launched, receives no further meaningful control from the engineers who built it. At 20% of light speed, communications lag between Earth and probe grows longer with every passing day. After 1 year of travel, commands sent from Earth take 73 days to reach the probe in interstellar space. After 5 years of travel, a round-trip communication loop takes over 2 years to complete at light speed. You cannot meaningfully steer something that cannot receive your instructions for months or years at a time. You point it at a star, you accelerate it, and then you let it go and hope it finds what you aimed at. Even if every technical obstacle were solved completely, this is what Breakthrough Starshot achieves. It sends a probe the size and mass of a postage stamp across 4.37 light-years of interstellar space. It cannot carry instruments capable of definitively confirming whether life exists on any target planet. It cannot decelerate. There is no braking mechanism, no fuel reserve, no way to slow down upon arrival. It is a camera attached to a sail, launched like a bullet, hoping to photograph a planet during flyby. That flyby lasts approximately 30 seconds before the probe shoots past and continues into deep space forever. This is the best idea humanity has produced for sending anything to another star in our lifetime. It is genuinely heroic engineering. It is also a precise measurement of how impossible the problem is. Now apply the same constraints in reverse to any hypothetical civilization targeting our solar system. To send a crewed spacecraft to Earth at 10% of light speed using the most efficient fuel theoretically possible, the required fuel mass using antimatter annihilation, the absolute maximum energy density available, would need to equal roughly the total mass of the planet Jupiter to achieve the necessary thrust. Antimatter is the most energy-dense propellant that physics permits under any known or theoretical law. Humanity currently produces nanograms of antihydrogen per year at CERN's facilities in Geneva, Switzerland. Scaling production to Jupiter mass would require building an energy infrastructure beyond all imagination. No known civilization, regardless of how advanced or ancient, sends crewed ships casually across stars. The energy constraint is not a temporary technical gap waiting for the right scientist to close it. It is a direct consequence of the same physics that constrains every other civilization equally and always. A ship traveling to Earth from 100 light-years away at 10% light speed spends 1,000 years in transit. The crew, if biological in any recognizable sense, ages and dies long before arrival comes into view. They would need generation ships, vessels where the founders' great-great-great-grandchildren arrive. Those descendants would arrive not as explorers representing a civilization they remember, but as strangers. Strangers arriving at a world that is no longer who their instruments observed when the mission launched. Let us map precisely the actual territory of humanity's electromagnetic presence as it stands right now. Our radio bubble has a radius of approximately 125 light-years, centered on our Sun in the Milky Way. Draw that sphere onto an accurate map of the galaxy and look at what the comparison actually reveals. The Milky Way's diameter is 100,000 light-years. Our bubble's diameter is 250 light-years across. Our bubble represents 0.25% of the galaxy's diameter, a single speck on a continent-sized map. In volumetric terms, we have announced ourselves to approximately 0.000002% of the Milky Way's volume. The universe contains an estimated 2 trillion galaxies beyond our own. We have reached none of them. We are not shouting into the void. We are whispering in a hurricane the diameter of eternity itself. Within the 125 light-year bubble, approximately 15,000 stellar systems fall within range of our signals. A 2020 study from the University of Nottingham estimated that at least 36 communicating civilizations may exist somewhere within the entire Milky Way galaxy at this moment in cosmic time. If 36 civilizations are spread across a galaxy 100,000 light-years in diameter, the average distance between any two of them is roughly 17,000 light-years from one civilization to its nearest intelligent neighbor. A message sent between two such civilizations travels for 17,000 years before it arrives at its destination. A round-trip conversation, question and reply, takes 34,000 years to complete at the speed of light. All of recorded human history covers approximately 5,000 years from the earliest writing to this moment. We are attempting conversations that would take 7 times the entire span of recorded civilization. The concept of any civilization arriving in time becomes philosophically incoherent at these distances. In time for what, precisely? We are not broadcasting a distress signal with an expiration date attached. We are simply existing, changing, evolving, producing, and destroying civilizations across geological time. Any probe or ship aimed at us is tracking a target that will not exist in its current form upon arrival. By the time any interstellar traveler could realistically complete the journey to our solar system, humanity as it currently exists would be as remote to our descendants as Homo habilis is to us today. Not figuratively remote, biologically, culturally, linguistically, technologically remote in every dimension. The geological timeline makes this inescapable when you examine it with complete precision and honesty. Homo sapiens as an anatomically modern species appeared approximately 300,000 years ago in Africa. The earliest human civilizations arose around 10,000 years ago, along rivers in the Middle East and Asia. Writing was invented roughly 5,200 years ago, the moment human memory first exceeded biological storage. Radio broadcasting has existed for 125 years, modern digital communication, less than 50 years total. Our entire technological civilization occupies 0.04% of the time our species has existed on this planet. The fastest transit achievable under known physics from Alpha Centauri, 437 years at theoretical maximum. In 437 years, English as spoken today may be unrecognizable, our political structures dissolved entirely. Any arriving civilization aimed at us now would not find who they set out to find. They never could. The distance does not just prevent arrival in time, it makes the concept of in time itself meaningless. There is one final dimension to this problem that even physicists rarely state with full directness. The Fermi paradox is not merely a puzzle about why we have not received signals from other civilizations. It is a mirror. It reflects back at us the implications of our own situation with perfect clarity. If we cannot reach them because of the wall of light and the abyss of distance and the tyranny of time, then they cannot reach us for exactly the same reasons, with exactly the same constraints under the same laws. The wall we face is the wall they face. The silence we hear is the silence they hear when they listen for us. The universe is not hostile to life. It may be filled with it, distributed across billions of worlds right now. But it has structured itself so that the filling is separated by distances no known physics can bridge. Within the timescale of a civilization's existence, within the biological lifespan of any living thing, we are not alone in a room, we are alone in an ocean, and the nearest shore is beyond the horizon of time. In 1998, economist Robin Hanson published a paper that changed how scientists think about silence. He called the concept the Great Filter, a barrier through which almost no civilization passes intact. The logic is straightforward, and the conclusion is either reassuring or catastrophic depending on timing. If the universe is ancient, vast, and physically hospitable to life, civilizations should be everywhere. The fact that we see none suggests something destroys them or prevents them before they become visible. The filter could lie behind us, in the brutal improbability of abiogenesis, the first living cell, or it could lie ahead, in some universal catastrophe that technological civilizations bring on themselves. If the filter is behind us, we are the rare exception and the future is open, however lonely it feels. If the filter lies ahead, the silence around us is a warning we are not yet equipped to understand. The distance problem interacts with the filter in a way that rarely gets explicit scientific discussion. Even if a civilization passes the filter and survives its own technology and continues to flourish, it still faces the same physical wall of light and distance that contains our own radio bubble today. A civilization 1 million years older than us, broadcasting continuously across 1 million light years, would be detectable to us only if they aimed a narrow beam precisely at our solar system on purpose. Omnidirectional broadcasts from even the most powerful civilization fade to noise within decades of travel. The mathematics of inverse square law does not negotiate with the age or sophistication of the sender. A million-year-old civilization shouting at us is still inaudible unless they whisper directly at us. The SETI program has implicitly assumed that civilizations broadcast broadly and continuously outward. That assumption may be the most expensive mistake in the history of the search for intelligent life. Dr. Frank Drake, who formulated the Drake equation in 1961 at a conference in Green Bank, West Virginia, built his framework on an era when radio broadcasting was humanity's dominant form of communication. That era is already ending. Earth's own radio bubble is growing quieter, not louder, year by year. Fiber optic cables carry our communications underground and under oceans, not into the sky above us. Digital compression makes our remaining broadcasts narrowband and harder to distinguish from noise. A civilization 125 light-years away, receiving our transmissions today, receives our 1900 radio era. In 50 more years, they will receive our early television. In 100 years, our digital compression silence. Our window of electromagnetic visibility may already be near its maximum and shrinking from here on. In 2021, a paper published in the Astrophysical Journal supplement modeled this transition explicitly. Authors Grimaldi and Bott calculated the expected radio visibility lifetime of a technological civilization. They found that leakage radiation creates a detectable bubble for only a few hundred years at maximum. After that, more efficient communication technology eliminates most of the electromagnetic leakage entirely. The radio era is not eternal. It is a brief phase that every communicating civilization passes through once. Like a match struck in a dark room, bright for a moment, then gone without a trace or a residue left. Any civilization looking for us must be looking at exactly the right moment in a very narrow window, and must be positioned close enough that the match is still burning when their light arrives to find it. There's a problem with interstellar contact that has nothing to do with physics or engineering directly. It has everything to do with how long biological organisms remain capable of maintaining a purpose. Human beings live approximately 80 years on average in developed nations in the 21st century. A generation, the time between a parent's birth and a child's birth, averages roughly 25 to 30 years. The shortest plausible interstellar journey to even our nearest neighbor takes thousands of years. No biological organism conceived today will live to see the arrival of any interstellar ship we launch. No biological organism will live to greet any ship arriving from even the nearest star system to us. This is not a solvable problem with better medicine or life extension technology at the margins. Even if human lifespan were extended to 500 years by radical biotechnology beyond anything current, the transit time to systems with confirmed potentially habitable planets runs to thousands of years still. The timescales of interstellar travel and the timescales of biological existence are incommensurable. They do not overlap in any range where a mission can be launched and completed within one life. Suspended animation has been a staple of science fiction for as long as space travel has been imagined. The concept appears in films, novels, and engineering proposals from serious aerospace researchers alike. The biology of suspended animation in complex mammals, however, presents profound unsolved challenges. Cells cooled below a critical threshold form ice crystals that rupture membranes and kill tissue. Antifreeze proteins exist in some organisms. Wood frogs survive freezing winters through biochemistry. Scaling these mechanisms to a 70-kilogram human brain without catastrophic cellular damage, unachieved. NASA has funded preliminary research into torpor states, reduced metabolic activity without full freezing. The SpaceWorks company proposed a 14-day torpor system for Mars missions in a 2014 feasibility study. Mars is 3 to 22 light-minutes away, depending on orbital geometry. Alpha Centauri is 4.37 light-years. The gap between a 14-day torpor system and a 6,000-year interstellar transit is not a gap, it is an abyss. Generation ships address this problem by giving up on individual survival and betting on lineage instead. The concept was described seriously by physicist Konstantin Tsiolkovsky as early as 1928 in Russia. Tsiolkovsky envisioned a spacecraft large enough for multiple generations to be born, live, and die within. The founding generation launches. They spend their lives raising the second generation on the ship. The second raises the third raises the fourth. Each generation inherits the mission and dies. Eventually, after 10 or 20 or 50 generations, descendants who never chose this arrive. They arrive at a star their ancestors aimed for. In a ship their great-grandparents built and launched. They have never seen Earth. They have never touched soil. They have never breathed unrecycled air. Their entire frame of reference is a metal cylinder moving through darkness that they have always known. The psychological and sociological challenges of generation ships have been analyzed in academic literature. In 2017, the American Journal of Bioethics published a detailed examination of generational ship ethics. The core problem: the founding generation consents to the mission, but cannot consent for future generations. Children born aboard a ship inherit a mission they never chose, in a vessel they cannot exit or escape. Every generation born on the ship is, in a meaningful philosophical sense, imprisoned from their first breath. The destination they are aimed at may be inhospitable by the time descendants arrive after centuries of transit. The society aboard the ship may fracture, transform, develop into something unrecognizable over generations. By the time arrival occurs, the civilization that launched the mission may no longer exist on Earth itself. The descendants arrive at an alien world representing a civilization that may have been dead for centuries. They carry forward a mission whose original purpose has outlasted the institutions that defined it. This is the mirror image of our own situation when we imagine a civilization sending a ship toward us. They face all the same problems in reverse: biological time, generational continuity, institutional memory. A ship launched from a civilization 50 light-years away arrives here after centuries of travel minimum. The descendants aboard that ship carry cultural memory of a world they've never seen and cannot return to. They arrive to meet a civilization that has changed beyond all recognition since the mission was conceived. The meeting, if it occurs, would be between two groups who have both been transformed by the transit itself. Two civilizations that no longer resemble the ones that made the original decision to reach across space. Here is the scenario that physics and mathematics genuinely permits under current and foreseeable technology. A civilization detects evidence of Earth either through our radio bubble or through biosignature analysis. They analyze our atmosphere from 40 light-years away and determine with certainty that life exists here. They point their most powerful telescope at Earth and detect the glow of our city lights on the night side. They watch our radio emissions rise, peak, and begin fading as we transition to fiber optic communication. They observe the chemical composition of our industrial civilization in the trace gases of our atmosphere. They know we are here. They know we are biological. They know we are technological. They know our address, and they cannot do anything with that information that would result in physical contact within any time frame that either civilization would recognize as relevant to the moment of discovery that initiated the search. The detection itself is a one-way window. They can see us, but the light carries no return address for us. We would not know we had been detected unless they immediately aimed a powerful directed beam at our sun. That beam, sent at the speed of light from 40 light years away, reaches us 40 years after they sent it. We receive it in 2065, having been observed in 2025. We reply immediately. Our reply reaches them in 2105. They receive confirmation in 2105 that their 2025 detection was correct, and we are aware of their signal. They now know we know. We now know they know. The two civilizations are aware of each other's existence. Between them, 80 years of light-speed messaging round trip. No physical object has moved an inch between stars. A conversation between them runs at 40-year per message intervals if both sides respond immediately each time. By any reasonable definition of contact, this is not contact. This is correspondence across geological time. In 2020, astronomers using the Parkes telescope in Australia detected a signal from Proxima Centauri. The signal, designated BLC-1 for Breakthrough Listen Candidate 1, caused immediate and serious excitement. It appeared at a frequency of 982.002 MHz, which falls within a range free of known natural radio emitters. It drifted in frequency over time in a way consistent with a source on a rotating planetary surface. Breakthrough Listen, the most generously funded SETI program ever attempted, investigated it intensively. After months of analysis in 2021, the team concluded the signal was almost certainly terrestrial interference. Human-generated radio frequency interference mimicking an extraterrestrial signal, a known and recurring problem. But for a period of months, the world's most advanced SETI researchers genuinely did not know what it was. The episode illustrated precisely how close the threshold of real detection is to impossible to confirm quickly, even with the source at our nearest neighbor. At 4.24 light-years, the analysis consumed months of debate. Real contact would not be a moment of sudden clarity. It would be years of agonizing data analysis first. The problem extends beyond detection into the domain of interpretation and meaning-making under uncertainty. If we receive an unambiguous artificial signal from 500 light-years away, what exactly do we do next? We cannot reply in any way that the sender will receive within a timescale meaningful to either civilization. A reply travels 500 years to them, their acknowledgement travels 500 years back. Total round trip, 1,000 years. The humans who crafted the reply will have been dead for 900 years by the time an answer could arrive. The civilization that sent the original signal may have transformed beyond recognition in the same millennium. Contact at 500 light-years is not a conversation. It is the exchange of time capsules across deep time. The content of those capsules would be addressed to descendants whose relationship to us is purely genealogical. In 2008, Chinese science fiction author Liu Cixin published a novel called The Dark Forest. It offered a disturbing proposed resolution to the Fermi paradox that has become widely discussed in science. The premise: every civilization in the universe knows that resources are finite and contact is dangerous. Any civilization that reveals its location risks destruction by a more technologically advanced civilization. Therefore, rational civilizations stay silent, concealing their existence as a survival strategy. The universe is a dark forest, Liu argued, full of hunters moving through the darkness in silence. Every civilization hides, and any civilization that speaks is immediately targeted and eliminated. The dark forest solution is logically coherent and internally consistent as a proposed resolution. It is also deeply incompatible with our own behavior since Marconi's first transmissions in 1895. We have been broadcasting our location, our biology, our technology, and our cultural content for 125 years. If the dark forest is real, we have been making the fatal mistake for longer than anyone alive has lived. The physicist Stephen Webb cataloged 75 different proposed solutions to the Fermi paradox in a 2002 book. They range from rare Earth to planetary catastrophe to zoo hypotheses to simulation theory and beyond. No single solution has gained consensus among researchers who study the problem seriously and systematically. Each solution has strengths that make it appealing and weaknesses that prevent it from being definitive. The rare Earth hypothesis, developed by Peter Ward and Joe Kirschvink, argues complex life is extraordinarily rare. It requires not just a habitable zone, but a large moon, a gas giant shield, plate tectonics, and specific chemistry. Each additional requirement multiplies the improbability of complex life emerging on any given planet. If complex life is extraordinarily rare, the Fermi paradox dissolves. We are simply alone, or nearly so. TRAPPIST-1 has 7 rocky planets, 3 in the habitable zone, orbiting a stable red dwarf star nearby. At 40 light-years from Earth, TRAPPIST-1 sits well within the radius of our expanding radio bubble today. Our 1985 broadcasts are arriving at TRAPPIST-1 right now, carrying Dynasty and the Challenger disaster. If anyone is there and listening and capable of receiving them, they are receiving them at this exact moment. There is a hypothesis among futurists and some physicists that rarely enters mainstream SETI discussion. It concerns what happens to a technological civilization in the period immediately after it matures fully. The hypothesis associated with Ray Kurzweil and developed by Vernor Vinge is called the singularity. The premise: technological growth accelerates exponentially until artificial intelligence surpasses human ability. Beyond that threshold, the civilization undergoes rapid transformation that biological intelligence cannot predict. Applied to the Fermi paradox, the singularity hypothesis offers a specific explanation for the silence. Civilizations that develop technology advanced enough for interstellar communication may quickly transcend. They may migrate from physical space into digital existence, simulated realities of their own construction. They may merge with their own technology in ways that eliminate any need for physical space exploration. They may simply lose interest in the cosmos because they have constructed an interior cosmos more compelling. A civilization that has built a perfect simulation has no reason to cross the hostile void between stars. They have everything they need inside their own computational substrate: beauty, complexity, challenge, meaning. From outside, such a civilization would simply go silent, not because it died, but because it went inward. The detection problem with post-singularity civilizations is that they would look identical to dead ones. A civilization that transcended into digital existence produces no interstellar signals we would recognize. A civilization that destroyed itself in a technological catastrophe also produces no interstellar signals. From our vantage point, using our current instruments, we cannot distinguish between these two outcomes. Both produce the same observable result: a star system that was once detectable and then went completely quiet. The silence around us could be a graveyard or a monastery, and we have no instrument to tell which it is. In 2021, a team at Oxford's Future of Humanity Institute published an analysis of Fermi paradox solutions. They found that the most likely explanation was some combination of life being rarer than optimists assume, and civilizations being shorter-lived or less detectable than the assumptions in the Drake equation suggest. Their Bayesian analysis showed that given the observational evidence, we should not be too surprised by silence. The silence is statistically consistent with life being rare, but not impossibly so across the galaxy. It does not require exotic solutions like the dark forest or universally catastrophic great filters. It simply requires that the optimistic assumptions in Drake's equation be somewhat lower than we hoped. Here is the deepest and most unsettling dimension of the entire problem of interstellar contact. We can only ask the question, where is everybody? Because we exist to ask it in the first place. Our existence is a data point. Our survival to technological civilization is an observation about the universe. But it is a deeply biased observation, because only civilizations that survived can observe their own survival. This is called the anthropic principle, and it corrupts our statistical reasoning in subtle, dangerous ways. We cannot conclude from our own survival that survival is common or probable across the universe. We can only conclude that it is not impossible, because impossible events have no observers to report them. Every civilization that failed to survive left no scientists to calculate how frequently civilizations fail. We are, by definition, the survivors, and survivors always underestimate the true rate of catastrophe. The anthropic principle applies directly to the question of who can receive our signals and respond. We assume that a civilization capable of receiving our transmissions is roughly analogous to us in structure. It has developed technology, maintained it, avoided self-destruction, and continued developing further. But the anthropic principle reminds us that we have no basis for assuming such civilizations are common. We only know they are possible because we are one. We cannot calculate the probability from one data point. The entire edifice of SETI rests on the assumption that our existence tells us something about general probability. That assumption has never been validated and may be the most fundamental error in the search's entire history. In 1961, Frank Drake wrote his famous equation on a blackboard at the first SETI conference in Green Bank. N equals R star times F minus P times NE times F L times Fi times F Nash C times L, 7 terms multiplied together. Each term estimates a fraction of stars and planets and conditions favorable to communicating civilizations. Drake himself estimated the product as between 1,000 and 100 million communicating civilizations in the galaxy. His optimistic estimate has driven SETI funding and imagination for 60 years of searching since Green Bank. In 2020, a revised analysis using updated exoplanet data and stricter biological assumptions by David Kipping at Columbia University arrived at a dramatically different estimate using Bayesian statistical methods. Kipping found that the probability of any given habitable planet developing a communicating civilization was most likely less than 10%, and potentially much lower depending on assumptions about intelligence arising. The Drake equation's terms are not fixed facts, but probability distributions with enormous uncertainty ranges. Change the assumptions by factors that remain scientifically defensible, and the answer changes by billions. The universe is 13.8 billion years old, measured with high precision by the Planck satellite mission. The first stars ignited approximately 200 million years after the Big Bang in the cosmic dawn period. The first heavy elements, carbon, oxygen, nitrogen, were forged inside those first massive stars. When those stars died in supernovae, they scattered the elements required for chemistry and biology. The first generation of stars contained none of these elements. They could not have hosted rocky planets. Rocky planets capable of hosting life required at least one generation of stellar death and rebirth. The Milky Way contains stars of all ages, some nearly as old as the universe, some forming right now. Stars that could host life-bearing rocky planets have existed in our galaxy for roughly 10 billion years. If life takes 4 billion years to produce technological civilization as it did on Earth, that is enough. Civilizations around the oldest suitable stars could have matured 6 billion years before we appeared. 6 billion years of additional technological development is an incomprehensible head start in every way. Any civilization 6 billion years ahead of us would be so advanced as to be invisible to our instruments. We would not recognize their communications as communications. We would not recognize their structures as structures. The night sky might be filled with the signatures of billion-year-old civilizations we interpret as natural noise. The astrophysicist Caleb Scharf at Columbia University has seriously proposed this as a hypothesis. In a 2016 article in Nautilus, Scharf suggested that advanced life might be indistinguishable from physics. A sufficiently advanced civilization might encode itself into the structure of matter and energy itself. It might exist as patterns in quantum fields that we mistake for natural phenomena without any suspicion. The dark matter that comprises 27% of the universe's mass energy content has never been directly detected. We infer its existence from gravitational effects, from how galaxies rotate and how light bends around clusters. Scharf asked, only half-jokingly, whether dark matter could be the medium in which ancient civilizations exist. The hypothesis is not falsifiable with current instruments and therefore sits at the edge of science itself, but it illustrates the critical epistemic point. Our ability to recognize alien intelligence is not guaranteed. We assume intelligence looks like us because we are the only intelligence we have ever encountered or studied. The universe may be full of conversations we cannot decode because we do not recognize them as language at all. It may be full of engineering projects we interpret as nebulae, signals we measure as cosmic ray backgrounds. The silence we observe may be a translation problem rather than an absence, and we have no way to know which. In 2016, the European Southern Observatory confirmed Proxima Centauri b using the radial velocity method. The planet orbits Proxima Centauri at a distance of 0.0485 AQ-Lutz, very close to the star's habitable edge. Proxima Centauri is a red dwarf star, dramatically smaller and cooler than our own Sun in every measurable way. Red dwarfs emit powerful stellar flares that could strip atmospheres from close-orbiting planets repeatedly. In March 2019, astronomers detected a massive flare from Proxima Centauri, 100 times more powerful than typical. Such flares could ionize the surface of Proxima b and drive away any atmosphere the planet had accumulated. Whether Proxima b is genuinely habitable remains deeply uncertain despite its confirmed existence in the zone. The distance to Proxima Centauri, 4.24 light-years. Travel time at fastest human technology, 6,100 years. In 2017, NASA's Spitzer Space Telescope confirmed the TRAPPIST-1 system has 7 Earth-sized planets. 3 of those planets, TRAPPIST-1e, F, and G, fall within the calculated habitable zone of the star. TRAPPIST-1 is 40.7 light-years from Earth, orbiting a red dwarf star in the constellation Aquarius. The system was discovered by Michael Gillon's team at the University of Liège in Belgium, using transit photometry. JWST has already analyzed the atmosphere of TRAPPIST-1b and detected no thick atmosphere on that inner world. Analysis of the potentially habitable planets in the system continues with each new observing season. Travel time from Earth to TRAPPIST-1 at Parker Solar Probe maximum speed, approximately 59,000 years. A signal sent to TRAPPIST-1 today arrives in 40 years. A reply returns in 2105 at the absolute earliest. In 2020, a team led by Dr. Kevin Wagner at the University of Arizona announced a candidate planet detection. The planet candidate orbits Alpha Centauri A, the larger Sun-like star in the triple Alpha Centauri system. If confirmed, it would be among the closest potentially habitable exoplanets to Earth ever discovered. Alpha Centauri A is 4.37 light-years away, essentially the same distance as Proxima Centauri from us. Our radio transmissions have been passing through that system since the early years of the 20th century. Every broadcast from the golden era of radio, every early television signal has already washed over it. If anyone lives there and was listening and had receivers sensitive enough to capture our fading signals, they have been receiving human culture for over a century. They have never responded with anything detectable. The Kepler Space Telescope, which operated from 2009 until 2018, confirmed over 2,600 exoplanets in total. Its successor, TESS, the Transiting Exoplanet Survey Satellite, launched in April 2018 and continues operating. TESS surveys the entire sky systematically, cataloging planets around the nearest and brightest star systems. By 2025, TESS has identified thousands of planet candidates within 300 light-years of our solar system. Within 300 light-years, our radio bubble has not yet reached even a third of these identified systems. We have found the addresses. We have not yet delivered the mail. The mail is still in transit, decades out. The universe is revealing its planetary population faster than our signals can reach the confirmed addresses. Let us do the final arithmetic that the entire problem ultimately reduces to when stated without sentiment. Our radio bubble is 125 light-years in radius. Our earliest detectable signals have a range of perhaps 2 light-years. The Milky Way contains at minimum 100 billion stars. Within 125 light-years, approximately 15,000 star systems. Of those 15,000 systems, an estimated 20 to 50% may host rocky planets in the habitable zone of their star. That gives perhaps 3,000 to 7,500 potentially habitable worlds currently within our radio bubble's outer radius. Of those worlds, what fraction developed life? What fraction developed intelligence? What fraction is listening? We have no empirical data for any of these fractions beyond a single data point, Earth, which is us. Using only one data point to estimate a probability is statistically meaningless by any rigorous standard. We can say the probability of intelligence arising is greater than zero. We cannot say how much greater. Even in the most optimistic, scientifically defensible scenario, say 1 listening civilization per 100 systems, we would expect perhaps 30 to 75 civilizations currently within our radio bubble capable of receiving us. Each of those civilizations received our signals between 1 year ago and 125 years ago, depending on distance. Each is processing that information on a timeline governed by their own biology and technology and culture. If any one of them responds immediately with a directed beam at our sun, we receive it years to decades from now. If any one of them launches a physical probe at maximum achievable speed, it arrives centuries to millennia hence. The gap between detection and contact is not a gap that any optimization or technology or will can close. It is the gap between the speed of information and the physics of matter moving through space and time. One obeys only electromagnetism, the other obeys mass, inertia, and the energy required to overcome both. No civilization, however ancient, however powerful, however motivated, has ever found a bridge across this gap. If such a bridge existed, wormholes, Alcubierre drives, quantum teleportation of matter, we see no evidence. We see no evidence in the physics, and we see no evidence in the sky of civilizations that built one successfully. The silence is not just an absence of signals. It may be an absence of exceptions to the rule of light speed. There is a name for the feeling this arithmetic produces when followed to its logical conclusion honestly. It is not despair. Despair implies that something expected and desired has been denied and taken away. What this produces is something closer to awe, a recognition of the scale of what existence actually is. We are a species that evolved on a pale blue dot orbiting an unremarkable star in an outer spiral arm. We have been broadcasting our existence for 125 years into a galaxy that has existed for 13 billion years. We have developed instruments sensitive enough to detect planets orbiting stars 40 light-years away. We have done this in the blink of an eye by cosmic standards in a fraction of galactic history. And the universe that we have revealed through all of this effort is not hostile, not empty, not indifferent. It is simply structured in a way that keeps its inhabitants in separate rooms without any connecting hallways. Each room is a solar system. Each corridor between rooms is measured in thousands of years of transit time. The rooms may all be occupied. The inhabitants may all be brilliant, curious, beautiful in their own forms. But the architecture of the universe ensures they will almost certainly never meet within any biological lifetime. This is not a tragedy in the conventional sense. A tragedy requires a hero and a preventable catastrophe. What the universe has arranged is closer to a permanent condition woven into the fabric of space-time itself. The speed of light is not a barrier that a sufficiently determined civilization eventually overcomes with will. It is the speed at which causality propagates, the rate at which the present moment influences the future. To exceed it is not to build a faster ship, it is to unmake the structure of time itself in doing so. We shout into the cosmos because we are a species that cannot help but reach toward what it cannot touch. We build instruments and aim them at the stars because curiosity is the deepest biological drive we carry. We calculate trajectories and signal strengths and round-trip message times because that is what we do. Because the alternative, silence and acceptance, feels like a betrayal of everything that makes us human. And perhaps that impulse itself is the answer to Fermi's question, if there is one to be found anywhere. Perhaps every civilization that reaches this level of understanding goes through this same reckoning alone. Perhaps the Fermi paradox is not a mystery to be solved, but a rite of passage to be experienced fully. Every intelligence in the universe, at the moment it becomes capable of asking, "Where is everybody?" discovers the same answer waiting for it in the mathematics. You are here, you are briefly visible, and you are alone. Not alone as in the only life in the universe, alone as in unreachably separated from all the other life there is. The universe is social by nature. It produces minds that reach toward each other across every medium available. And it is structured by physics in a way that prevents those minds from ever quite completing the reach. That tension between the impulse to connect and the physics that prevents it is the condition of all intelligence. It is our condition. It may be the condition of every mind that has ever existed in this vast and ancient cosmos. We are 125 light-years of signal in a universe 93 billion light-years wide. We are a single candle in a hurricane. We burn as brightly as we can. We send everything we are outward into the darkness at the speed of light. And somewhere, perhaps, something receives us, measures us, wonders about us, and faces the same wall we face. The wall that physics built at the beginning of time and has never once permitted any exception to pass through. In 2022, a team of scientists sent the most powerful deliberate transmission Earth has ever broadcast. The Beacon in the Galaxy message was designed by Dr. Jonathan Jiang at NASA's Jet Propulsion Laboratory. It built on the 1974 Arecibo message, but incorporated 48 years of additional scientific understanding. The team encoded mathematics, chemistry, biology, and an invitation to respond at specific coordinates. It was aimed at a region of the Milky Way with high stellar density, maximizing the number of potential receivers. The transmission was sent using the FAST telescope in China, the world's largest single-dish radio telescope. FAST has a collecting area of 500 meters in diameter, dwarfing every previous radio transmission facility. The signal was aimed at a stellar cluster approximately 1,000 light-years from our solar system. The earliest any civilization in that cluster could receive it, the year 3022, over 1,000 years from now. The earliest any reply could return to Earth, the year 5022, 3,000 years into our future. The scientists who designed and sent the message understood completely that they would never hear a reply. They sent it anyway because the message was not really for whoever receives it in 1,000 years. It was for us. It was an act of collective human declaration. We are here. We have not given up reaching out. The content of the Beacon in the Galaxy message reveals something important about how we see ourselves. It opens with mathematical axioms, prime numbers, binary arithmetic, universal constants that transcend culture. Mathematics is the only language that any intelligence capable of receiving the message would also speak. A civilization advanced enough to detect a radio transmission is advanced enough to recognize prime numbers. The message includes the biochemical structure of DNA, our molecular autobiography encoded in binary data. It includes a map of our solar system with Earth indicated as the origin point of the transmission. It includes representations of human figures, our size, our bilateral symmetry, our basic physical form. And it includes coordinates and a timestamp, allowing a receiver to know exactly where and when we sent it. The message is a complete introduction from a species that knows it may never meet the recipient in person. It is humanity's most careful attempt to be understood across the unbridgeable gap of interstellar distance. What the Beacon in the Galaxy message cannot solve is the fundamental problem of signal decay over distance. At 1,000 light-years, even FAST's enormous power advantage over Arecibo fades dramatically with the square law. The signal arrives at its destination as a whisper at the edge of detectability by any known receiver technology. A civilization at 1,000 light-years would need a receiver array the size of a small planet to capture it cleanly. We are not sending a clear signal. We are sending a hope that something sufficiently sensitive is already listening. We are dropping a message in a bottle into an ocean and hoping the currents carry it to exactly the right shore. The search for the optimal message format has occupied information theorists since the 1960s without resolution. Hans Freudenthal, a Dutch mathematician, published Linkos in 1960, a formal language designed for cosmic contact. Linkos used mathematical logic as its foundation, building progressively toward more complex concepts. It assumed that any receiving intelligence would share the fundamental structure of logical inference with us. That assumption may be the most optimistic in the entire history of SETI, and it may be the most necessary. We have no empirical basis for knowing whether alien intelligence reasons in ways compatible with our mathematics. On Earth, mathematics emerged from counting, from measurement, from the needs of agriculture and architecture. An intelligence that evolved under radically different physical conditions might have developed differently. A civilization that evolved in a gas giant's atmosphere, without visual light as a primary sense, without solid ground. Its mathematics might be based on pressure differentials and chemical gradients rather than geometric shapes. Its logic might operate on principles we would not recognize as logic from within our own cognitive framework. The message we send assumes we share enough cognitive architecture to decode each other's transmissions. That assumption is reasonable. It is also completely untested by any contact we have ever actually made. This moment, this specific second as you receive these words, is itself a moment of cosmic transmission. Somewhere in the sky above you, radio waves are escaping Earth's atmosphere and heading outward at light speed. A streaming service's satellite uplink, a cellular tower's ambient leakage, a weather radar pulse, each of these is adding to the expanding sphere of human electromagnetic presence in the universe. The sphere is growing at the speed of light in every direction simultaneously from our small blue planet. Right now, our 1963 transmissions, Kennedy's assassination, Beatlemania's first radio broadcasts, are washing over star systems approximately 62 light-years away at this exact moment you are reading this. Any civilization at that distance with a sufficiently sensitive receiver is currently receiving 1963. They are, right now, in their equivalent of this moment, potentially detecting human civilization for the first time. We will not know this for 62 years, the time it takes their discovery signal to reach us at light speed. The present moment of Earth's broadcasts is always arriving somewhere new in the universe for the first time. Every second, our expanding bubble crosses new star systems that have never before received any signal from us. We are continuously and permanently making first contact with the galaxy 1 light-year per year at a time. The question is not whether we are discoverable. We are discoverable. We have been discovering for 125 years. The question is whether discovery, at these distances and under these physical laws, can ever mean anything more. Can it mean more than a civilization receiving a faded record of who we were before either of us can respond? Can it mean more than 2 bubbles of electromagnetic presence expanding through space, possibly overlapping briefly, without the civilizations inside them ever being able to reach through the bubble wall and touch each other? The light we are sending right now carries everything we are. Our arguments and our music and our mathematics. It carries our wars and our kindness, our stupidity and our genius, compressed into radio frequency patterns. It will arrive somewhere eventually in a form too faint to hear without extraordinary technology to amplify it. And whatever receives it will face the same impossible arithmetic we face when we imagine receiving theirs. The arithmetic that ends always in the same place, too far, too slow, too late for physical contact to follow. Detection without arrival is the true condition of intelligence in a universe governed by the speed of light. It is the condition we are in right now with every star we observe. We see them as they were, not as they are. The light from Alpha Centauri that reaches your eyes tonight left that star 4.37 years ago. The light from the Andromeda Galaxy reaching your eyes tonight left that galaxy 2.537 million years ago. You're not seeing the universe as it is, you're seeing the universe as it was, a layered fossil of time. And any civilization seeing Earth through a telescope tonight is seeing us as we were, not as we are today. They see a version of us frozen in the past, separated from the present us by years or decades or millennia. The universe is not a place where things exist simultaneously and can perceive each other in real time. It is a place where light carries information slowly across distances so vast that simultaneity loses meaning. By the time any signal connects 2 minds across interstellar space, the moment that created it is gone. This is perhaps the universe's most fundamental and most overlooked feature as a home for intelligence. It is a universe that produces minds capable of contemplating the cosmos in extraordinary, intricate detail. And it is a universe that physically prevents those minds from ever meeting the other minds they contemplate. Every civilization is an island. Every star system is surrounded by a moat of years and decades and centuries. The moats do not dry up with better technology, they simply become slightly more crossable at greater cost. The cost in energy and time and biological life always exceeds what any individual civilization can pay. Thank you for staying with this journey to the edge of what physics permits and what civilization dares to dream. If this left you staring at the sky, subscribe and stay for every question the cosmos has not yet answered. Your curiosity is the only thing in this universe that genuinely travels faster than the speed of light allows.